All right, good morning, guys. So 10.1, in Unit 10, we're going to be looking at square root functions and maybe some other stuff. I don't remember. So this is what a square root function graphs as. All right, we basically see a curve that increases at a decreasing rate. And notice that this line starts at 0, 0. There's a reason for that. So basically sorry about that. Let's get this back. So basically with these square root functions, there's a couple of rules that you got to remember with the radical. So basically what it says is a square root function is a function that contains a square root with the independent variable in the radicand. We'll talk about that vocabulary in a second. The most basic square root function is y equals the square root of x. So when we're talking about a square root symbol, all right, the symbol itself is called the radical symbol. So this is called a radical symbol. That's what a square root symbol, that's the official name of it. And the value or expression inside the square root symbol is called the radicand. Okay, and the big thing that we need to remember here is that the radicand, this can never be negative. Okay, so this cannot be negative. Okay, now the important thing to remember here is that the entire value of that radicand cannot be negative, but you could have like an expression in there where you put a negative number in and it winds up being positive, and that's okay. So the domain, so the radicand can never be negative. That's important to know. So radicand, let's write this right here. Radicand cannot be negative. And the reason for that is if you try to square root a negative number, you wind up getting an imaginary number because it's not real. And you'll learn about that in Algebra 2 when you guys are sophomores. Radicand cannot be negative. And then the next thing is the domain of a square root function is basically, where was it? Domain is all real. Let me look at it again. Sorry. So the domain of the square root function includes x values for which the radicand is greater than or equal to 0. So let's put that. So the domain includes x values where the radicand is greater than or equal to 0. And we'll talk about that down here in this first section. Okay, so finding the domain of a square root function. All right, so we have this square root function, y equals x minus 5. If we want to find the domain, we basically, they're asking us which x values will show up on this graph or which x values are going to work. So what we're going to focus on is literally this right here, this radicand. So we're going to take the radicand, which in this case is x minus 5, and we're going to set this greater than or equal to 0. And the reason for that is because that radicand cannot be negative, okay? So we set it greater than or equal to 0 to figure out which x values will work for this function. And so to find the domain, all we have to do is solve for x. So we're going to add 5 to both sides. So in other words, the domain is going to include all x values greater than or equal to 5. And this is the domain. All x values greater than or equal to 5. If we were to graph this, like what we would see is a graph, something like this, where this line is going to start at 5 and then it's going to horseshoe up like that. And it's not going to include any other x values because it can't be, the radicand cannot be negative. Now, on a an example like this next one where the plus 7 is outside of the radicand, we don't include that. So in this case, we're just worried about x. So basically the domain is going to be the radicand. Okay, so we take the radicand and set it equal, greater than or equal to 0. And so the domain in this case, we don't have to do any work. The domain is going to be x is all greater than or equal to 0. So all x values greater than or equal to 0. That's what we state. All right, so the next skill we're looking at actually graphing and comparing two square root functions. So we're going to just we're going to offset this since we're only talking about positive numbers here. We're going to offset it so we can graph these pretty easily. So let's start with the easy one, which is y equals the square root of x. Okay, this is your most basic square root function. And we're going to just make a quick table here. So we'll do x, y. And we're only going to pick x values that can be square rooted. So we'll start with 0. Remember, the radicand cannot be negative, so we're not going to do any negative numbers here. Okay, so we're going to start with 0. And the square root of 0 is 0. Okay, and then we can go to 1. The square root of 1 is 1. Then we can go to 4. The square root of 4 is 2. And then we can do 9. The square root of 9 is 3. So we'll go ahead and graph that, and I'll do red for this one. Okay, so 0, 0, 1, 1. And then we start to see it stretch. We go 4, 2. And then 9, 3. Okay, so there's our most basic square root function. Okay, we just have a line that's increasing at a decreasing rate, and it's because those x values are stretching it. So they want us to compare this to y equals x plus 3. So let's see what that plus 3 is going to do here. So y equals the square root of x, and then the plus 3 is outside of that radicand. So we're not concerned with it. So we're just going to pick the same numbers for x. It's not affected by that plus 3. So we'll just do 0, 1, 4, 9. And all we're doing is just adding 3. So square root of 0 is 0, plus 3 is 3. Square root of 1 is 1, plus 3 is 4. Square root of 4 is 2, plus 3 is 5. Square root of 9 is 3, plus 3 is 6. Okay, so we're at 0, 3, 1, 4, 4, 5, and then 9, 6. And so what we see, if we were to compare these two, the only difference here is the y-intercepts. All right, and that plus 3, when there is a number outside of the radicand, this is a vertical shift. It just changes the y-axis. So if it was plus 3, we move up 3 units. If it was minus 3, we move down 3 units. And we call that a vertical shift. So when we have a operation or a plus or minus operation outside of the radicand, it's a vertical shift in the direction that you think it would go. So all we did was move up 3 units. So plus 3 units on everything. All right, so let's look at the next one. Compare negative the square root of x minus 2. Describe the domain and range. And we didn't really do that up here. So the domain of both of these would be x is greater than or equal to 0. And the range of this first graph we put on here, that would be y is greater than or equal to 0. And the domain of the second line right here would be y is greater than or equal to 3. Okay, and we can write that down here. Well, it doesn't matter. You get it. Okay, so let's talk about this first. Well, let's go ahead and graph y equals square root of x. And this time I'm going to just put the x-axis centered, because I think the negative is going to throw us for a loop a little bit. Okay, so we already know how to graph y is equal to the square root of x right there. So we'll put that, we got 0, 0, 1, 1, 4, 2, and 9, 3. Okay, so there's our first line. So the domain of this would be x is greater than or equal to 0, and y is greater than or equal to 0 as well. That would be the domain range of that first one. Let's look at the next one. So y is equal to negative the square root of x minus 2. Now, this minus 2 is inside the radicand this time, so that's going to change things. We need to pick numbers for x that are going to work well here. And you can do just like a quick, set this radicand greater than or equal to 0. So x is going to need to be greater than or equal to positive 2 once you solve that. So we know that our values for x that we pick need to be 2 or greater. Okay, we don't want to pick anything less than that because otherwise we're going to wind up with a negative radicand which can't be solved. So what I'm going to pick then for x is I'm going to do, let's see, I think we can do 0. Nope, because that's less than 2. Let's do 2. We're going to start with that. Okay, so 2 minus 2 is 0. Square root of 0 is 0. So that negative on the outside isn't going to change anything. There's no such thing as a negative 0. Okay, and then we can do 3. 3 minus 2 is 1. Square root of 1 is 1. And that negative changes it to negative at the end, so negative 1. And then we can do 6. 6 minus 2 is 4. Square root of 4 is 2. So that's going to be negative 2. And we can stop there. That's good enough. So we're at 2, 0. So right here. That's where we're starting at. And then 3, negative 1. And then 6, negative 2. Right there. I think the next one we'd want to use is 11. Would be the next value because when you subtract that, you get 9. So comparing these two, basically what we see here is that when we have an operation happening inside the radicand, plus or minus operation happening inside the radicand, this is what we call a horizontal shift. All right, horizontal shift meaning we shifted not up or down, but we shifted left or right. And it's actually opposite of what you would think because that minus 2 caused us to go to the right 2 units. Okay, so this was minus 2, which you would think, well, minus 2 should make us go to the left. But with horizontal shift, it's opposite of what you think it is. Whereas with vertical shifts, it's exactly what you think it is. Okay, so the velocity y in meters per second of a tsunami can be modeled by the function y equals the square root of 9.8x, where x is the water depth in meters. Use a graphing calculator. At what depth does the velocity of the tsunami exceed 200 meters per second? Okay, so they tell us to use a graphing calculator here. I would argue that that's a lot harder. So if we put this in a graphing calculator, so second square root of 9.8x and we graph that. Let's zoom. Let's do square. What we see on this, that doesn't help me. What's going on? Standard. There we go. What we see is a much more drastic curve. That 9.8 basically stretches this line. Okay, we're going to see a more drastic increase initially. Okay, whereas the normal square root function is a lot flatter than that. So that 9.8, when we're multiplying x by a number inside the radicand, it stretches things. So if they want me to, so they ask me, at what depth does the velocity exceed 200 meters per second? Well, y is velocity, okay? And so they're asking me, when does this get more, or when does the depth, or at what depth does the velocity exceed 200? So they want y to be greater than 200. And they're asking us basically x, which is depth. At what depth does that work? If I were to do this, guys, like, I could click the trace feature and I could try to get y to 200, but I mean, like, that's going to take forever to use the trace feature. So I would just encourage you to use the function. So basically, we just take this and we do 9.8 x. Okay, and the so like the, hold on one second. So if I'm gonna plug, let's just say we'll just plug 200 in here. I'm gonna just work through this. So I'm gonna do inverse operations here. Let's square both sides. So 200 squared which I have right here. So 200 squared is 40,000. And then I have that equal to 9.8x. Okay. And then, where did I go? Okay. So now I'm going to divide that by 9.8 and I get 4,081. So I know that at 200, x equals about 4,081. So we could basically just increase that, and then we just round it up like 4,100. That's when x is about when x is going to equal. Because and the reason well, I mean, you don't have to round it that high. We want to round it up because we know this thing is increasing. So, and we want it to be greater than 200. So we could say at about 4,100, or you can say like, 4,082, x is or y is going to be greater than 200. So you could say, either one of these answers, depending what they ask you for, would be approximate, valid answers. And that's basically the water depth when the tsunami reaches more than 200, or exceeds more than 200 meters per second. So all we did was plug in y, solve for x, and then we just rounded it up a little higher, and that gives us an approximate answer. Now you could literally trace the entire graph until you got to y was more than 200, but that would take forever. This is an easier way to get a good estimation. All right, that's it, guys. Thanks for watching.